given the centroid of this cross-section, determine the moments of inertia of this cross-section. So the first step here, as Joe astutely pointed out, would be to determine the location of the centroid. So what I'll do is I'll break this up into two different sub-areas, two different primitive areas. So I'm going to have a primitive area up here, which is the top flange, and I'm going to have a primitive area down here, which is the web of the section. So I'll call this my first sub-area. I'll call that my second sub-area. And then what I'll do is I'll define my datum as the bottom. So if I were being more consistent, I would probably call this capital Y bar. And then I have a centroid here to the centroid here to the first area. So this would be little y bar sub 1. And then I have a centroid here to the web. And this would be little y bar sub 2. So then what I can do is I can come in and I can say that y bar is equal to the sum of a sub I times y bar sub I divided by the sum of a sub I. So if I write that out, then what I get is 12 times 4, and then multiplied by this distance is going to be 16 plus 4 over 2, so that's going to be 18 inches. And then for the lower part, we have 16 inches times 2 inches for the thickness, and then multiplied by 16 over 2 is 8 inches, like that. And then down here, we just have the area, 12 inches times 4 inches, plus 16 inches by 2 inches, like that. So we would end up with, let's see, so 12 times 4 gives me 48. And then 18 times that gives me 864. And then we have 16 times 2 gives me 32.0. And then I multiply by 8 and I get 256. And multiply those, I get 1,120 inches cubed divided by 48 plus 32 gives me 80 inches squared, and my value of y bar is equal to 14 inches. Okay, so I know that this value here is 14 inches. So now what I can do is I can figure out what the moments of inertia are. So what I'm going to do is start off, I'm going to write the moment of inertia I of little x sub 1. Now what is little x sub 1? That is the centroidal axis that goes through the centroid of area 1. And then in a minute you're going to have this. This is going to be the x-axis that goes through the centroid of sub-area 2. Let's do 1 first. So we can go through here. That's a rectangular shaped area, and we know now that that is equal, the moment of inertia is equal to BH cubed over 12. So this is going to be, the base is going to be 12 inches. The height is going to be 4 inches. Cube that divided by 12. So let's see, 4 cubed times 12 divided by 12. Yep, I actually typed that in my calculator. 64 inches cubed. All right. And then we take I sub x2. That's equal to the base times the height of that primitive divided by 12. In this case, the base is 2 inches. The height is 16 inches. That's cubed divided by 12. And let's see, so 16 cubed times 2 divided by 12 gives me 682.7 inches cubed. Oops, should be inches to the fourth. Yep, thank you, Max. I saw that pop up and I'm like, shit, I made a mistake. And there it is. Okay. Let me double check that number. So 16 cubed divided by 12 times 2. Yeah, 642. All right, now you would be tempted here to say that I sub big X, okay, where is the big X axis? This is the big X axis, is equal to I sub little x1 plus I sub little x2. But that is just not true. This is absolutely false. The only time that that is true is when the two axes are actually collinear. When the x1 axis and the x2 axis line up with each other, then you can add them together. So what we need to do is we need to convert these first before we can add them together. We could say that the moment of inertia I big X is equal to the moment of inertia of subarea 1 about the big X axis. And then we can add that together with the moment of inertia of sub x2 about the big X axis. So this is correct. This will work. So what we need to do then is use the parallel axis theorem. And now we could say that this is I sub big X is equal to I sub little x1 plus a1 d1 squared plus I sub little x2 plus a2 times d2 squared. So we interject the parallel axis theorem. We're going to convert from I sub little x1 to I sub big x1. We're going to convert from I sub little x2 to I sub big x2, and then we're going to do that. So let me go here. I'm going to go back up here and try and fit this all on one slide. So I sub big x1 is equal to, I already calculated it, 64.0 inches fourth plus the area. This is going to be the area of sub primitive 1, so 12 times 4. And then this distance, let me go ahead and write that in there. This is the distance here, d1. And I don't have a ton of space, so I'm just going to write it in here. So that was 16 plus 4 over 2, or 18. So it's going to be 18 inches minus, and then 14 inches here, and then squared. So let's see, 64. See, it's going to be 4 squared times 4 times 12. And then 64 plus that gives me 832. And that's inches fourth. And then here, I'll write I sub big X2, and that's equal to 682.7 inches fourth. And then now I have plus the area there, that's going to be 2 inches, times 16 inches, and then times the distance. And the distance here is going to be 14 inches minus 16 over 2, or minus 8 inches. And let's see, so we get 14 minus 8 gives me 6. I square that, multiply by 16, multiply by 2, and then I add in 682, and I get 1,835 inches fourth. And now I can add those two together, so I could say that I sub big X is equal to big X1 plus I sub big X2, and that's equal to 2,666 inches to the fourth.